On the last slideshow, we looked at qualitative examples of horizontal accelerated motion, point particle. Let's get into some quantitative problems for horizontal accelerated motion. So the first thing you want to do is you're going to ask yourself some questions. And the first one is this a constant velocity situation? You read the problem, you determine is there acceleration involved, or is it a constant velocity situation? Well, what's usually going to happen is it's usually going to be a little bit of both. It's going to have constant velocity parts and constant acceleration parts. So essentially, when you find that out, you are having to break the problem into two parts. So let's take a look at an example of some of these problems. First one we're looking at is the train coming to the station, moving at a constant speed. So that's your constant velocity part. Town's 1 kilometer away. 30 seconds, the conductor applies the brakes. What acceleration is necessary to bring the train to rest exactly at the edge of town? So the first part is a constant velocity, or also what we call uniform motion problem, where we use velocity equals delta x over delta t. And then the second part of the problem is uniform accelerated motion. Notice this is one of the equations I asked you to memorize, and you copied yesterday in class, or maybe earlier, depending on when. So delta x equals v squared over 2a. So this is what we're going to use, because we can use this version of the equation because the train is coming to a rest. So convert 1 kilometer to 1,000 meters. Start with the constant velocity section. Here comes the train. So we want this train to stop before it runs the town over, the villages over, runs through the train station, whatever. So the conductor is going to apply the brakes just at the right time to stop this train. So we'll figure out, okay, first of all, if it's 1,000 meters before we get to this town, let's see how much ground is covered going at constant velocity. So 12 meters per second for 30 seconds means that this train has covered 360 meters. So that's this portion right here. So the next thing we're looking at is this constant acceleration portion where the conductor is braking the train. And so we're going to use our delta x equals v squared over 2a. So at this problem here, you have to look at this problem and say, okay, well, what was the velocity before it came to rest? It was 12 meters per second, so you'll put the 12 in here, and then the delta x goes here, and then you're solving for a. I've algebraically rearranged this problem for you already. I plugged in the variables, and then here's our final answer, 1.1 times 10 to the negative 1 meters per second per second. So what does the negative sign indicate? What do you think that negative sign means? You know what it means. It means that the train was heading to the right, but it was slowing down. That means the acceleration sign is to the left. This is the race between the horse and the human. And on the next slide, I'll circle key piece of information and discuss how to tackle this problem. So I'm going to go ahead and forward. If you want to pause here, take a look at this problem, that would be terrific. Here we are. So the first part of the race, it's a sprint. It's a 400-meter sprint between a horse and a human. And the first part of the race is constant acceleration. And then after the acceleration is done for both the horse and the human, each one finishes a race with constant speed. So it's a 400-meter race, and what we're trying to figure out is how much of a head start time would the man need in order just to tie the horse. So what we really need to do as far as time is concerned, we need to figure out how long does it take for the human to finish the entire race, how long does it take for the horse to finish the entire race. And the first question that you need to ask yourself, if you recall from the beginning of this slideshow, was, is this constant velocity? Is this uniform accelerated motion? And as you can see, it's both constant speed, constant acceleration. So we're going to have to use our tools to tackle this problem. So let's start with the human first. So starting from rest, starting at the 0 meter mark, the human accelerates at 12 meters per second every second. And in the problem it told us this happens for 1 second. So what I do is I start the problem with the uniform accelerated motion equation that we can use since the sprinter starts from rest. Delta x, or d equals 1/2 at squared. I use delta x because the displacement is horizontal. Plug in the numbers. 6 meters of the track is covered during the acceleration phase. And we're not done. We have to use this piece in our other acceleration equation. Delta x equals v squared, that should be squared up there, over 2a. So I've rearranged this to find the velocity, and the velocity at the end of 1 second is 12 meters per second. So this shouldn't surprise you, since this human is accelerating at 12 meters per second every second. If the runner started at 0 meters per second, after 1 second, they're going to be going 12 meters a second. So some of you may recognize that, or you may need to rewind and hear me say that again. So remember, acceleration is the rate at which velocity changes. And from 0 to 12 meters per second for this particular human, whether you're accelerating, is a 12 meters per second squared, or 12 meters per second acceleration. So the constant velocity piece. We determined that during this portion of the race, the acceleration motion, the human went 6 meters. So we're going to take that from the 400. There's 394 meters remaining. We also need to take this final, this velocity that was the end velocity during the accelerated piece, because we're going to have to pop it over here into the constant velocity, because the runner is going to run 12 meters per second for the rest of the race till they get to 400. So you have to recognize that, and not only solve for it over here and recognize, oh, well, I'm having to solve for that because I got to use it over here. So now we have 394 meters left. The velocity of the human's 12 meters per second. We're going to use our constant velocity equation. Velocity equals delta x over delta t. Rearrange for t, 33 seconds. So it takes the human sprinter a total of 34 seconds to run this race. 1 second for the accelerated motion piece right here, and 33 seconds for the constant velocity piece. We do the same thing for the horse, except 4 seconds, 6 meters per second for 4 seconds is the acceleration for the horse. So I'm going to go ahead and move on to the next slide. You can pause it here if you want to take a look at the information, or get your calculator out and do the problem yourself. See if you're capable of running through each of these equations and plugging in the information. Takes the horse sprinter 19 seconds total between the 4 seconds during uniform accelerated motion and the 15 seconds during the constant velocity phase. Final answer, 15-second head start for the human. For the human and the man to just tie at the 400-meter mark.